All right, so let's close the loop on the central limit theorem. I'm really excited about how we're using Python, and you notice homework 6, I asked you to submit it as a Jupyter notebook. Now, whether you use scipy.stats or not, it's up to you. There was a couple of problems where I asked you that you must use scipy.stats, so I expect you to do that. On the other ones, you're welcome to use that, and I think you should. You know, it just kind of simplifies everything in one place. And what we did with the CLT, I think, was nice as we set the stage for the rest of this course, because the capability of doing simulating an experiment is incredibly powerful. That's what we did last time. We were trying to demonstrate the central limit theorem. If you remember, we rolled a die 300 times. We created an array of those rolls, and then we sampled from those and tried to demonstrate that the central limit theorem is true. We're going to continue building on that today, and as we move forward, we will use that approach to verify the theory that we are learning, right? So in practice, you're not going and doing 1,000 samples from a population to demonstrate that the mean of the sample is equal to the mean of the population. No, that's going to be a given to you. When you go and pick a sample from the population, you expect it to be close to the population mean when you pick the mean of a sample, but you just pick one sample, right? What we're doing here is verifying or demonstrating that this is true, that you could do that, okay? So that's what we're doing here, and that is going to be the power of an engineer versus a technician who has a certificate in data science. For this problem, do that. For that problem, do that. You don't want to be that kind of person. You're engineers. You think deeper than the average person who knows data science or statistics, okay? So I'll go back a little bit to definitions, and then we'll pick up from there. We said that we were talking about sampling distributions. That was our primary thing we were dealing with, and we said a sampling distribution is the distribution of any statistic of the samples that you're looking at. In other words, if you go pick a bunch of samples from a population and say you're looking at the average height of those people, or the average width of the wall in your manufacturing facility, or the average defect in your guitar necks that you're manufacturing, right? So, or the variance in those, or the quartile, any statistic on a sample, okay, is going to be fair game when you look at the distribution of that statistic across different samples. A sampling distribution is therefore the frequency distribution of a given statistic across all possible samples. So this is theory. We're trying to build the theory so that in the future, when we pick one sample out of a population, what can we infer about the population? But first, to make that inference, we need to learn how samples vary in a population, right? So that's why we say in theory, across all possible samples, the sampling distribution is the probability or the frequency distribution of any given statistics. So it could be the sampling distribution of the sample means, the sampling distribution of the sample variances, the sampling distribution of the sample quartiles, whatever statistic you can pick on a sample. And when you do that statistic across all possible samples, if you could in theory, then that's called a sampling distribution. What we learned in the simulation that we did last time, and in the intuitive example that we together built intuitively, we were looking at the sampling distribution of sample means. Okay, so now when I say sampling distribution of sample means, you are looking at plotting. If you're thinking of a plot, you're plotting the means of all possible samples, okay, the means of all possible samples, and looking at the frequency distribution of those means. So it is a probability distribution, okay? And the theorem, the theorem that we were all kind of looking out for, it's called the central limit theorem, says that for any given population, whether finite or infinite, with a given mean value mu and a standard deviation sigma, the shape of the sampling distribution of sample means will approach that of a normal distribution. So that's an incredible result, all right? And then so now you take the means of all samples, like we did last time, and you plot the histogram, okay? What is the mean value of those means? It's going to be equal to the mean of the population. That kind of makes sense. because you're taking the mean of the mean is going to be the mean. Okay? The mean of the mean is going to be the mean, right? So it doesn't change because it's a constant. But the standard deviation of the sampling distribution of sample means, so now sample means, you see this x bar, bar indicates a mean, x is this from the sampling distribution, is going to be equal to the population standard deviation over square root of n. Now next I'm going to ask a question later for why this is not equal to that one and why it doesn't make sense for it to be equal to that one, right? Now, I said in practice a sample size needs to be large enough, larger than 30 in common practice, and the larger the sample size, the better that the normal distribution approximation will be. So now, if the following conditions are met, if you have a sample size of more than 30 and you have a bunch of sample means, then you can use this property that the mean of the sampling distribution of sample means is equal to the mean of the population. If that's given, then you can infer this one. And the standard deviation of the sample means is going to be equal to the standard deviation of the population, if you're given this, over square root of n. Okay. Now, eventually, we're not going to know those information. Once we hit inferential statistics, you're going to be dealing with a population for which you don't know the mean nor the standard deviation. And we're going to use this theory to infer those properties about the population, okay? All right, so given this result, now I want to go back to my simulation and check in Python that my sample means are equal or close to the true population mean. Now this is in the limit that we have a very large sample, so n equal infinity, approaching infinity, or the entire population, right? Which we didn't. In our sampling example, we did 40, we pulled out with replacement 40 die faces from the population, right? So n is greater than 30, but certainly not infinity, right? But as we increase that sampling size and also increase the number of samples, because this is true for all possible samples, then we should approach the mean value of our sampling distribution, should approach that of the population, and the standard deviation of the sampling means, the sampling distribution of sampling means, should be close to population standard deviation of a square root of n. So let's check that. Again, I'm doing a demonstration. This result, we will not use it like this. You're not going to sample all samples. You're not going to take samples to infinity. You're not going to do that. But I'm demonstrating the theory here that will allow us to do crazy things later, like just take one sample and make a generalization about the entire population. Okay, they tell you don't make generalizations. Well, in statistics, darn it, we're going to make generalizations if you do your sampling correct. That was nicely. Okay. Okay. All right. So let's check this in Python. Grab your Jupyter notebooks. Kind of hurt a little bit, but okay. Let's grab our Jupyter notebooks and go back to our simulation. I think I still have the file open. It's in class simulation of fair die. Okay, so I'm going to move this to Creston. Okay. And I'll give you a short reminder of what we did here. First, zoom in a little bit. So we imported our boilerplate from SciPy, etc. We're done with this. And then we said we're going to roll a die 300 times. And we used numpy.random.randint to create a random integers from 1 to 6, right? 300 times, 300 of those. Okay, if you remember, this die rolls contained all possible print die rolls, if you forgot. Okay, and so it just contained an array containing the different phase values of the die roll. So on the first roll, we got a 6. Second roll, we got a 5. Then here, we had a sequence 1, 1, 1, then 4, 4, 3, 3. It's just random with equal chance of landing any one phase, because this is a fair die. Okay, so we know that's true, and Python can do that very accurately. Okay, so this randint gives you that approach, and then we plotted the histogram, and we got this sampling. This is the population distribution, sorry, not the sampling distribution. And, you know, up to a decent approximation, we're pretty much uniform. There's an equal number of 1s, equal number of 2s, equal amount of 3s, equal amount of 4, approximately in that array, in that bag, in that population. All right. Then what we did, step 3, to demonstrate our central limit theorem, is we said, okay, we're going to take 5,000 samples of this population with replacement. So sample, what does a sample consist of? I'm going to reach into the bag and grab a number, record it, and then put it back. And then grab another number, record it, and put it back, and so on and so forth. I'm going to take 40 numbers per sample. And then do the same again, and do the same again. And for each sample, I'm going to record what I got out of the bag. All right, now to do this, I do numpy.random.choice. So I'm choosing from the population of die rolls, I'm choosing 40 pieces with replacement. And I'm going to do this 5,000 times. Okay, that's going to be, because we want to get close to all possible samples. How many samples there are of size 40 in a population of 300? A very large number. Okay? So 5,000 samples is nothing compared to how many samples I got of size 40 in that population of 300. Then I compute the mean for each sample, and then I store those sample means. All right? And then when you plot the histogram of those sample means, this is what we did last time, the central limit theorem is saying that the sampling distribution of the sample means, or the histogram, or the probability distribution of the sample means, is going to look like a normal distribution. And it does. It does. This histogram is talking about the sample means. In other words, the means of those samples are distributed like this. On the x-axis is the mean value, and on the y-axis is the probability of getting that value, okay, or the count of getting that value, depending on what you do on the y-axis, right? And we would expect that we should be 3.5 as the maximum probability. So around here gives us this value about 1.3, 1.4. So we're getting there. We're approximating that theorem in this demonstration. Okay. Now, what I wanted to test next is, let me delete all of this here. Okay. What I want to test next is the results of this theorem that say that the mean of the sampling distribution, we have the sampling distribution now. It's our histogram. That's it. We're done. We picked 5,000 samples of size 40 each, and we plotted those. That's it. That's our sampling distribution. Okay? This is saying that the mean of the sampling distribution is close to the population mean. Now, should be equal in the limit as the number of samples approaches the total, all samples, and n approaches. If everything is exactly the same, then you're going to get that exactly equal. But in practice, it's not going to be equal. In next chapter, we're going to learn how far off they're going to be. But for now, let's accept that they're going to be pretty close to each other. All right? Let's go ahead and do this. And first, we need to compute the, so let me add checking CLT results. Okay. So let's first compute the population mean. Okay, compute the population mean, and that will be, so let's say pop mean is going to be np.mean of die rolls, right? And if we print that, print pop mean, it is 3.49333333. Okay? That's the true mean of the population. It's not a statistic for a population, it's a property. It's not a statistic, it's a property of the population. Okay. So now we need to compute the mean of the sampling distribution of sample means. Okay? So sample means, that's going to be np.mean. Okay, so where did we store our sample means? Here. right? Sample means is an array that contains the mean values of all the samples. I'm just going to take the average of that, the mean value of all mean values. And should be close to the population mean. Let's see how close it is. np.mean of sample means. Okay, let's print population mean equal pop mean, and then print sample mean, sample sampling distribution mean is equal to sample, it should be mean of sample means. Mean of sample means. I don't want to confuse the, sample means. All right. So look at that. The population mean was 3.49. The sampling distribution mean is 3.4, almost 3.37. So we're getting close. It's not exact, and that's actually an important result. Now, in the limit as increases and the number of samples increases, we're going to get close. So let's test that, right? Our hypothesis is that, yes, as n approaches infinity and across all samples, we should get close to the population mean. All right, so let's try that out. So we're going to go back here, and we're going to keep this as is. The population doesn't change. I'm going to do 10,000 samples now, and maybe do 50 in the sample size. Okay, you do this, and look at that. Guys, it's insane. It's getting close. The population didn't change, but the sampling mean change is almost close, 3.492, 3.493. It works. It works. It should. Yes. Okay, now what about the standard deviation of the sampling distribution? Okay, so let's compute that. All right, so now compute the standard deviation of the population. Now remember, there's a difference between standard deviation of population and standard deviation of a sample. So we need to pass that information on to Python. Okay? And the way you do this with NumPy, it's really great. Pop std is equal mp.std for standard. It says compute the standard deviation of a distribution. All right, so it's got a bunch of things. A is the array, and then a bunch of features here. None of those I care about except for this one, DDOF. Now, DDOF will tell me if this is either a population or a sample. Okay? DDOF, degrees of freedom, or delta for freedom. So how many degrees of freedom do you have? For a population, we have no degrees of freedom. It's going to be 0 by default. So for a population, you put DDOF equals 0. So we're going to do, this is going to be die rolls. And DDOF, by default, it assumes it's a population. Okay? And then now compute. Okay, so this is good. We have the standard deviation of the population. Next, we want to compute the observed standard deviation of the sampling distribution of sample means. All right, so this is going to be sample means std, and this is going to be np.standard deviation of the sample means, right? This is a distribution of the sample means, so I'm going to compute the spread of the data in this histogram, in other words. Okay, and for that, I am going to put sample means, that entire array, and is going to have a degree of freedom of 1 because these are going to be samples, right? These are going to be samples. Okay. Now this is not enough because what we've done here, so I computed this and I computed this numerically. But I need to verify the theory that this the observed value of this is equal to this over square root of n. So let's do that. See what I've done here? All right, so this is the observed. Now compute the theoretical STD of the sampling distribution. Sample means STD, or theoretical sample means STD. It's simply equal to the population standard deviation over how many, what's our sample size? Here, sample size is 50 over MP dot square root of sample size. Clear? So now I have an observed standard deviation of the sample mean that I collected and a theoretical estimate of what this should be. The theoretical estimate says it's equal to the population standard deviation over square root of sample size. This one just computes just a bunch of numbers. It computes the standard deviation for those numbers. Okay, so let's copy and paste these printout statements and put them down here. Okay, so this would be observed standard deviation, and sample means STD, and this would be theoretical standard deviation, and this would be theoretical. All right, look at that. Theoretically, the theorem is telling us that this variance or the standard deviation in your sampling distribution is going to be population standard deviation over square root of n. What we've observed in practice is this value, and they're pretty close. They're going to get closer and closer and closer. In other words, this value is going to get closer, or they're going to get closer to each other in the limit. But it's important that they're different, because this is where probability comes in when we do inferential statistics. Because we're going to know that in practice we only have a limited size sample, not an infinite sample. What we need to know is how different these estimates are going to be. We'll do that starting in the next chapter. So right now we're just learning the tools, verifying things, right? Doing simulations, statistical simulations. Okay. They ask you, what did you do today? We did statistical simulations. It's really cool stuff. Okay. Okay. Let's check this in Python. All right. So as an outcome, this tells us that the sampling distribution of sampling means has the same mean as the original population, but the standard deviation of sample means is much smaller than the standard deviation of the original population. So it's the original population standard deviation over square root of n. Would we have expected that? Yes, because the sample means are a different measure of what the population is looking at die faces. The sample means is looking at the average role the average role that you will get in these roles. So they're going to be more closely packed towards the central value or the central mean value. So this variance of the standard deviation of the sampling distribution of sample means is going to be much smaller than the standard deviation of the original population. They're measuring different things. Okay, the original population is thus die faces. The sampling distribution is the mean of those roles. Okay? All right. Now, what's also mind-blowing is that this result, this whole thing, is also true for a population with any probability distribution. So I kind of slipped that under the radar at the beginning when I put a fair die, and you might have said, as a good scientist, engineer, you could say, well, this is only true, you're lucky here because the original distribution is uniform. It's a fair die, there's a fair equal likelihood of any phase occurring, so blah, 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 whatever math is going to work out, and you're going to get this result. No, it doesn't matter. It doesn't matter. The original population can be distributed however you like. Could have a pear shape, whatever shape you want. This result is still going to be true. How about we demonstrate that in Python? Okay, so you learn another trick on how to create custom probability sampling distributions. All right, so let's do this in Python. So what we're going to check now is if the die is not fair, and whatever probability you want to assign to that, we're going to create that, make a population of an unfair die, and then make sure that we're going to get the same result. Okay, so let's do this. So what I will instruct you to do is make a copy of your Jupyter notebook. Go ahead and didn't they have a duplicate option? Where? They used to have a duplicate or make a copy. Okay, we'll just let's actually go here. Let's go here, see if I can duplicate it here. Okay, so if you go to your to the home of your where this is, you can duplicate it. Okay, there you go. It's duplicated here. Or you can just create a new notebook and copy paste the contents. Okay. I'm going to bring this back to my. Okay. All right. So this is a duplicate, and we're going to call this simulation of unfair die. Okay, so we're going to make an unfair die here. Now, this is going to be a little bit different than what we did with randint. We have to use another function in NumPy, another routine in NumPy that will allow us to create 300 rolls of an unfair die. Okay, but first we need to create biased probabilities. So step 0, I guess. Step 0, create an array of biased die probabilities. Okay, so let's call them biased probabilities. And it's just a simple list. So let's say whatever you want. Just give me, let's make it very unfair. Like let's say phase 1 is going to be 80% chance of landing on phase 1. Go extreme, okay? I don't want it to be on the center, because if it's centered on the center, then the population will look like a normal distribution, and the results is going to be consistent with a normal distribution anyway. So let's make it weird. Let's make it peak at phase 1 and then flatten out at the other phases. Okay, so for phase 1, we're going to assign an 80% probability. For phase 2, we're going to assign a 5%, let's say, and then 2.5%, 2.5%, and then 0.9, and then 0.01, let's say. Okay, now these biased probabilities, let me do it up here. You need to make sure that they sum up to 1, right? There you go. Right? So you make sure that the probability rules are satisfied. The total of all probabilities are going to sum up to 1. Now, what does this array contain? These are probability of landing 1, 2, 3, 4, 5, 6 on an unfair die. Right? So if I roll this unfair die, there's an 80% chance I'll get 1. Okay, 5% chance I'll get 2, 2.5% chance I get 3, and so on. All right, this is great. Now, I also need, for what I'm going to do, I will also need to declare the faces of my die. This is just how it works with the approach that we're gonna use. Just trust me on this for a second, then becomes clear when we use that tool. So I need to declare an array for die faces, and I'm gonna make that, let's just make it a NumPy array. We can make the other one a NumPy array too, it doesn't matter. And we're gonna, the options that we have are 1, 2, 3, 4, 5, 6, okay? If you had, you could put whatever you want here. This is what I'm trying to build now, is a pool of options with associated probabilities for each of those options that I can sample from or make a population out of. Okay? Now, if you put here 6, 5, 4, 3, 2, 1, then 6 is going to have an 80% chance, and so on. So make sure these are consistent with each other. Okay? Now, the number of entries in this probability distribution should be equal to the number of entries in this one, because we have one probability value for each one of those values. Okay? All right. Now, step one, generate 300 rolls from an unfair die. All right. So how are we going to do this? I'm going to call this unfair die rolls. Interestingly, numpy.random.choice, which allowed us to do sampling from a distribution, also allows us to create a population with a specified probability and a specified pool to choose from. Okay, so let me show you how. If you do np.random.choice, if I look at the function signature, this is going to generate a random sample from a given 1D array. In this case, I'm creating my population from the 1D array of 1, 2, 3, 4, 5, 6 with those given probabilities, but I'm going to do that 300 times. And it's just going to do that for me. Now, if you look at the options here, size, we're going to do 300, and we're going to choose from 1, 2, 3, 4, 5, 6. What is P here at the end? P, the probabilities associated with each entry in A. So my input array is going to be the die faces, 1, 2, 3, 4, 5, 6, and the associated probabilities, and I'm going to choose 300 of those based on those probabilities. So internally, it's like it's rolling an unfair die 300 times. Okay, so let's try this out, see what it does. np random.choice, we're going to do die faces in this case, and size equal 300, and P is biased probabilities. Okay. So, or size equal total rolls. Total rolls. So let me comment these out for a second. And I want to print unfair die rolls. Now, if this is true, in this array, what are we going to see? What face are we going to see the most? 1, because it has an 80% chance of occurring. So let's test this. Die faces is not defined. Oh, come on. There you go. Oh, look at that. There's so many ones in here. Yep, that works. Does the job. Approximately 80% of those values are ones. What's up, Soren? I executed the cell before. Yeah, it wasn't defined. Just read the error. Okay? Okay. So now we can plot and verify the distribution with a histogram. Now we have unfair die rolls. Actually, if I call it die rolls, then I don't have to change anything further, right? Because everything is going to look the same. So just call it die rolls, not unfair die rolls. Aha, look at that distribution. There's a very high chance that one is going to occur versus all the other faces. And let's make this a density histogram. So density equal true gives us a true probability. Look at that. The probability of getting one is hovering around 80%. Okay? Go ahead and change that distribution on your Jupyter notebook. Make sure they sum up to 1. Okay? So I'm going to, let's go try it out. Let's say I'm going to flip those. I'm going to put 0.8 over here and 0.01 here. Okay. And look at that. For phase 6, it gave me 80%. Okay. However you want to put it, doesn't matter. Now the rest is the same. We should be able to run it. And the sample means what? They're going to follow a normal distribution. Let's try it. This piece here runs all of the sample means. And look at that. Ain't that a miracle? It is a normal distribution. It's different than the one with the fair die because it has a different mean. Look at here. The mean here is close to 1.5. The other one it was close to 3.499, whatever. Right? But it's still a normal distribution. Different mean, different standard deviation. Okay, so now let's check the results of the CLT. Population mean 1.573. Sampling distribution mean 1.575. Spot on. Go ahead, play with the probability of the unfair die. Still going to be the same. Let's look at the standard deviations. The observed standard deviation 1.5757. The theoretical prediction is 0.1750. An incredibly useful result. How are you not excited about this? Like in my heart is like I'm having palpitations. Like this is the most significant thing I learned in the last couple of years. Like this is so exciting. I mean, I've known of the CLT, right? But doing this simulation and demonstrating this, right? This is fun, man. And imagine they derived all of this just with the power of their intellect, right? Just pen and paper. Now we can demonstrate it with Python and can observe it, right? Okay. Now you can plot a normal distribution on top of this. Okay, you can just define a normal distribution, give it this mean value and the standard deviation, and it will plot it on top of it. Okay. We're not going to do that because we need to get back to the lecture slides. Okay. Perfect. So now we deduce that a normal distribution may be used to approximate a sample distribution of sampling means if the sample size n is at least 30, in which case the central limit theorem applies. But there's also the degenerate case if the population itself is normally distributed, then this is true regardless of the sample size. Why is that true? Why a random sample from a population who's distributed normally is also a normal distribution? That's by definition of the random variable and the random sample. If your random sample is a true random sample, then that sample is going to be normally distributed or is going to have the same PDF as the original. A true random sample will have the same, that was in one of the definitions, right? If you go back to one of our definitions here. Okay, random samples and also has the same probability of being selected, or each random variable has the same PDF as the population. So if the population is a normal distribution, then your sample means are also going to be normally distributed. By definition, no need for n. Okay? So that's kind of the key result here to move forward, to use this, is if n is greater than 30, then you can use the central limit theorem. If the population is normally distributed, then you can use the result of the central limit theorem as well. Okay. Now, how do we apply this? Again, if either the sample size is at least 30, I want to make a point on the 30 thing. So one of your colleagues last week asked me, like 30, that seems low. Like, what if you're sampling, 7 million people? Do you pick a sample of 30? Of course not. Because a sample of 30 for 7 million people is not going to be a random sample, right? If your population in a city is 7 million people, choosing 30 is not going to be a true random sample. So in that case, your sample has to be bigger. Now, how do we deduce that number? We will see in the next chapter. Depending on the error you're willing to commit in your analysis, that will help dictate what the value of n should be, okay? But typically, the population size will tell you, 30 people out of 7 million is hardly going to be a true random sample. So you'll need more. But at least it's going to be more than, like maybe you figure out, okay, I'm going to have to at least sample 1,000 people to cover all districts in my city. Well, that's greater than 30, so definitely the math is going to work out, okay? Now, if you think of the sampling means as represented by this x bar, and the sampling means the sampling distribution of sample means has a mu x bar and a sigma x bar, then you can build a standard normal distribution by building the z-score. And then we get back to our tables, which were so simple to work with, standardizing the normal distribution. As you saw in the example we did, we had two different normal distributions with different populations because the means were different, etc. But you can standardize those by building the z-score for each one of those sampling distributions, and then you'll normalize everything to a normal distribution of mean 0 and standard deviation 1, right? So keep that in mind. And now this would be the z-score for the sampling distribution. It's x bar, the mean of the sample, minus the mean of the population, per standard deviation of the population divided by square root of n. As we go through the semester, we're not going to know mu or sigma, okay? But we're building up to that point, okay? Let's figure out how to work with these so that later we can just make conclusions and inferences about population means and standard deviations. Let's start with an example. And this example will illustrate to you an important point. Let's see what it does. So according to the CDC, most people say the Center for Disease Control and Prevention is actually the Centers for Disease Control. There's apparently many of those centers, sometimes they're useful. So the mean total no, this is going to go on YouTube. Of course, they're very useful for everyone. So the mean total cholesterol level for persons 20 years of age and older in the US from 2007 to 2010 was 197 milligrams per deciliter. Right? Now, the first question is, what's the probability that a randomly selected adult from the population will have a total cholesterol level grams per deciliter? Use a standard deviation of 35 milligrams per deciliter and assume that the population, the cholesterol levels are normally distributed in the population. Okay, so we don't need central limit theorem theory here. The original population is normally distributed. This is a standard chapter 6 problem, standard normal distribution problem. What is the CDF for x equal 183, or you get the z-score and you compute the area to the left, okay? So if this were our cholesterol distribution, on the x-axis you have the cholesterol, and the y-axis you have the probability density. This is 197 for this area, probability that it's less than 183 milligrams per deciliter. Then you can get a z-score, so you can use the tables, or you can just put this into Excel or Python, and you get a z-score. From the z-score, you get the probability of about 34.46%. Okay, so then the probability of just one adult, no sample means no nothing. There's 34% chance of picking a random adult with a cholesterol level less than 183 milligrams. That's for one person. Okay. Now the next question is going to be, what is the probability that a randomly selected sample of 150 adults from the population will have a mean cholesterol level less than 183 milligrams? So this is the same question, but now we're asking the question on a sample, not on an individual. So we're going to pick a sample, random sample of 150 adults, get their cholesterols, compute the mean. What is the probability that that mean cholesterol value is less than 183 milligrams? So this one gave us 35% chance, 34.4% chance. What is this going to give us? Okay. So you go ahead and get the z-score. Now our x bar is 183 because we're looking at the sample mean. They told us what's the probability that the mean cholesterol of that sample is 183. You compute the z-score for that, you get minus 4.9. Now remember, in the tables, anything below minus 3.4 or above 3.4 is 0. There's no area. So in this case, there's 0 probability that you pick a random sample of 150 adults with a mean cholesterol of less than 183. That's insane. If you pick one adult, there's a 34.4% chance that that adult has a cholesterol less than 1.83. But if you pick a sample of 150, there's a 0 chance that they have a cholesterol less than 183. It's probably more, right? But that's how statistics work. Okay, distinguish the difference between an individual and a sample. Okay, and these are the questions that we will be asking in statistical inference. We're going to go the other way around, though. We're going to ask the sample, what is your mean value? What is your standard deviation? What does that mean on the population? Okay, because that's the practical application of this. Elevators are required to have a weight capacity posted. Who reads those weight capacities? Well, I go in, I'm always curious to read the weight capacities. I avoid elevators as much as I can. I don't like being confined in it, especially when they have glass. I mean, they're so cool, but I'm like, when I look down and around, I do not like that. Like all things come to mind. What if the cable breaks, snaps, and what if the brakes don't work? And like, should I like float, jump up, or like lie down? Like, yeah. And we actually we had an incident in my family where the elevator crashed 3 floors. Yeah, we're kind of nervous about elevators. So if the weight of US men are normally distributed, so the weight of US men has a normal distribution. Okay, so we're dealing with normal distribution. No need for central limit theory yet. The mean value is 194.7 pounds. So the average weight of US men is 194.7, and a standard deviation of 32 pounds. What is the probability that a random group of 10 men who enter an elevator will have a combined weight greater than the weight capacity of 2,000 pounds that is posted in the elevator? So you have this elevator that has a limit of 2,000 pounds. We know the weight distribution of US men. What's the chance that a random group of 10 men entering this elevator would have a combined weight capacity greater than 2,000 pounds? Now, this is phrased a little differently, okay? Although the sample size, although the sample size is less than 10, I already mentioned that this is normal distribution, so no need for central limit theorem. Because the population is distributed normally, a random sample of 10 people is going to be distributed normally. Their weights are going to be distributed normally as well, so we can use the result that we have. A normal approximation is not needed. Now, we can calculate the sample mean. Remember, we're looking at averages now. So they didn't give us the average. What is the average weight of the person, of the man going into the elevator? But we can compute that. We have 10 men, a weight capacity of 2,000. 2,000 over 10 gives you 200 pounds on average. Okay? So in other words, the question is, what is the probability that a randomly selected group of 10 men have a mean weight greater than 200 pounds? Okay? Because 10 men, mean weight 200. 200 times 10 is 2,000, so that's the limit, the weight capacity. What's the chance that their average weight is more than 200 pounds? And if you look at the probability distribution, we have 194.7 as the mean value. We're looking at the area above 200 pounds. Right? So you compute the z-score and get the probability. And there's a 30% chance that these guys might crash the elevator. Next time you see 10 dudes going into an elevator, do not go in the elevator with them. Okay. All right, let's see this one. I mean, this is kind of coming back to the exercises we've done before. But we're looking at sample means now, all right? Not probability of individuals, right? We're looking at sample means, proper statistic on a sample. Suppose that the prices of athletic shoes have a mean value of $75.15 and a standard deviation of $17.89. What is the probability that the mean price of a random sample of 50 pairs of athletic shoes will differ from the population mean by less than $5? Okay? So differ by less means area in between. Differ by more, it's area in the tails. Remember that. Okay? So we're saying here, differ from the mean. So if this is the mean, differ by $5, $5 to the right, $5 to the left. It defines these boundaries. And we can calculate these numbers from the mean value plus $5 minus $5, get the z-scores, and then compute the area. And a 95% chance that this is true. Okay. The only thing we're doing differently here than what we did in the last week is that we're looking at samples, not individuals. The procedure is identical, except you're dealing with a sample. Okay? All right, should we do this one more example and then take a break? Oh, okay, a local hardware manufacturing plant. The screws being manufactured have a mean length of 1.625 inches with a standard deviation of 0.01 inches. If the quality control director randomly chooses a batch of 50 screws, what's the probability that their mean length differs from the mean of the population by more than 0.004 inches? So, which is the maximum tolerance allowed. So this is a quality control issue, which as an engineer you will be dealing with. All right? So what's the chance that if you randomly pick 50 screws out of this plant, you're only allowing a tolerance on average of 0.04 inches, okay? What's the probability that the mean length differs by more than this? Okay, so again, so now we don't know the distribution of the screw length, and it doesn't matter. Because we have 50 screws, we can apply the CLT. Okay, so I don't care anymore about the original distribution, right? This is great. So like imagine when we were 4 weeks ago trying to figure out the sample space to calculate probabilities. This is great. I don't need any sample place or any of that, just a sample size, and I can trust the CLT. I have a normal distribution. I use continuous math, and I get answers. All right, so this differs by more than 0.04 inches. So this is going to be areas in the tails, right? This is the mean 1.625 plus 0.004 minus 0.0024. I want to find these two areas, okay, over here. I get the z-score. How do you get the z-score? It's your sample mean minus the population mean over the sampling distribution standard deviation, which is sigma over square root of n or square root of 50. You get your z-scores, you calculate the area, there's a half, and you compute this from the tables or whatever, and you get a 0.5% chance that this is going to be the case. Very low probability. You're good on your quality control, right? And you can move on with life. All right? If you want to take a couple of minutes break, the next is I just have a few, or I can cover the slides, and then you can go home, whatever you want. Slides, and you can go home. Okay, good. All right. Now this is not. We're probably not going to use this a lot, but I thought I'd cover it, and it's covered in the textbook. And note some of the material that I scatter here is not always in the textbook, so I use a couple of other textbooks as well. But you know, easily learnable. We can apply the central limit theorem to proportions. So like oftentimes you would ask questions, you know, if 95% of the people are voting this way or that way, what is the likelihood that 20% do this or that, right? So these are proportions. And you can apply, there's a version of the central limit theorem on proportions. And I can tell you the answer right now. For continuous variables, the central limit theorem gives you a normal distribution. For proportions, it gives you a binomial distribution. But guess what? We can approximate the binomial distribution as a normal distribution. So that's what we're going to do. Okay? So for proportions, you simply take the number in your population or your sample and divide it by, so for a population, you take the value in the population and divide it by, so 50 people divided by total, by 1,000, all right, or by 100, whatever is in your total population. And for the sample, we call the value in the sample, so divided by the total size of your sample. So that gives you a proportion, okay? The value of the proportion goes from 0 to 1 or 0 to 100%. Okay? Now, when samples are taken are simple random samples, the conditions for a binomial distribution are met. Okay, so sorry, let me go back here. The CLT states in this case that the distribution of sample proportions, not sample means, sample proportions follows a binomial distribution. Okay, now the binomial distribution, we can compute that, but it would be nice to just move everything into a normal distribution because we have a standard normal distribution with one table or just one function, one routine that can compute all of those. Turns out, remember, we talked about approximating the binomial distribution with a normal distribution, if you remember that. Then you could say if the following conditions are met, that n times p is greater than 10, and n times 1 minus p is also greater than or equal to 10, then you can use a normal distribution to approximate the binomial sampling distribution of sample proportions. With the original CLT, the sampling distribution of sample means follows a normal distribution. With the proportions, the sampling distribution of sample proportions follows a binomial distribution, which can be approximated by a normal distribution under these conditions. And then, if you remember what we did with the binomial, when we moved from binomial to a normal distribution, then these would be the conditions here for your normal distribution. The mean of the sample proportions is P, is that probability of the flipping a coin of the single trial. And the standard deviation of the sample proportion, if you remember, we had this square root of P times 1 minus P divided by square root of n. So this, you're going to carry a square root of n in the denominator from the central limit theory. And then you can build a z-score the same way we built a z-score for mean value, for sampling means, except now we have sampling proportions. And you just have to figure out what mu is, which is simply P, and the proportion in the original population over the standard deviation for the sampling proportion, which is this guy. Once you do this, you're back in business. Okay, so here's an example. In a certain conservative precinct, 79% of the voters are registered Republicans. So there's a story about this, how they screwed up a poll when Roosevelt was running for re-election. I think I was reading about this yesterday, and it was a total disaster. It actually bankrupted that magazine because they really missed the mark. Like the opposite of their prediction turned out to be true because they had a mess in their samples. I'll probably put it as an example next time. So 79% of voters are registered Republicans. What's the probability that in a random sample of 100 voters from this precinct, at least 68 of the voters would be registered Republicans? So we know that in this precinct, there's a 79% chance, okay, so that's your P. Okay, that's the population probability. Voters are Republicans. Then if you pick 100 voters at random, what's the chance that 68 of those 100 would be registered Republicans? Since we're working with proportions, we need to get the sample proportion, which is 68 over 100. That's 68%. Okay? That gives you your P hat. Your P is 79%, and then your N is 100. The Z-score, minus 2.7. We're looking at the area to the right. Because we're saying what's the probability that at least 68% are registered Republicans. Getting the area to the right, and simply from the table, you get 99.65%. So that's the CLT with proportions. We were never told anything about the distribution of voters in that precinct. And it doesn't matter, because we know that the CLT for proportions is going to give us a normal distribution approximation. Okay? And with that, we'll be done. So you'll have, what, a 15 minutes break to stretch your legs. All right? Godspeed. I'll see you on Thursday.